must be equal. If they are not equal, the limit does not exist. Alright, we have seen all this. Let's use that to make our general statement. Now, although the limit at x equal to 2 exists, the limit as x get closer and closer to 2 from the left and the right are both the same. Therefore, we say the limit exists. Well, but what is the value of f of 2? If you now put x equal to 2, you can see nothing comes out. That means f of 2 does not exist. You can see there's a hole there. And if you go to your calculator and do a calculation of the function at x equal to 2, the calculator will tell you y equal to, I don't know. There is no output. F of 2 does not exist. You see, the limit from the left exists, the limit from the right exists. Both limits come closer and closer to 4. So limit from the left equal to limit from the right. But the function value at x equal to 2 does not exist. That means the function is not continuous at that x value. There you are. You can see that hole right there. So therefore, we say the function is not continuous at x equal to 2. Now, look at the function f of x equal to x plus 2. Now, what is the limit, the limiting value of x plus 2 as x get closer and closer to 2 from the left? You can see x plus 2 is a continuous function. So it doesn't matter whether x is approaching from the left or approaching from the right. Its value will be 4, because what all we need to do in a continuous function is to replace x by the value of c. So that limit will be 2 plus 2, that is 4. How about limit x approaches 2 from the right of x plus 2? Again, this is a continuous function. Replace x by your c and you get 4. And also f of 2 equal to 4. Now, isn't this beautiful? The limiting value of this function at some c value. This is a c value we have. C is 2. You can see here, I have used 2 here, 2 here, and 2 here. That is our c value. As x get closer to some value c, if the limit from the left equal to 4, the limit from the right equal to 4, and the value of the function at that c value also equal to 4. Well, that means the function is continuous. The limit from the left equal to limit from the right equal to the function value, and that means the function is continuous at x equal to 2. So if I ask you, what is the condition for a function to be continuous at x equal to c, what will you tell me? In order that a function may be continuous at x equal to c, the limit x approaches c from the left must be equal to the limit x approaches c from the right, must be equal to the function value at x equal to c. Then we can say the function is continuous. There you have the graph of f of x equal to x plus 2, and it is continuous all along. There is no hole anywhere. A function f of x is continuous at x equal to c if, can you complete that for me? What are the conditions necessary for a function f of x to be continuous at x equal to c? Well, the limit x approaches c from the left of the function must be equal to the limit x approaches c from the right of the function, must be equal to the value of the function at c, f of c. Now, this is the necessary condition for the function to be continuous at x equal to c. It is not enough that the left limit equal to the right limit. We had it in an earlier case. but also the function value must be equal to that limit for the function to be continuous. Now we found that there are certain discontinuities in certain functions where the domain, depending on the domain values, if there are some domain values that are not allowed. In some cases, the discontinuities can be removed. Now, for example, this we saw, f of x equal to x squared minus 4 over x minus 2 is not continuous at x equal to 2. But you know, we talked about that. But we can simplify this. What is x squared minus 4? X squared minus 4 can be factored as x minus 2 times x plus 2 and divided by x minus 2. You notice that x minus 2 and x minus 2 will cancel. Actually, this rational function is the same as x plus 2. And you know, x plus 2 is continuous everywhere. Whereas x squared minus 4 divided by x minus 2 is not continuous at x equal to 2. Why? They are both the same. But when you have it in this form, there is no output for x equal to 2. That means this discontinuity can be removed by this algebraic process. What we have done is we have removed the discontinuity by factoring and cancelling the common factors. So f of x equal to x plus 2 is continuous as x plus 2. That means we have removed the discontinuity there. Alright, try this. Remove the discontinuity and find or evaluate limit x approaches 1 of x squared plus x minus 2 over x squared minus 1. You see, if you now replace x equal to 1, what will you get? 1 squared plus 1 minus 2, that will be 0. And 1 squared minus 1 is 0. It will be 0 divided by 0. What is 0 divided by 0? Has no meaning. So, this has a discontinuity. At what point? At x equal to 1. Because at x equal to 1, the denominator becomes 0. But we can actually remove that discontinuity by algebraic process. What is that algebraic process? We can factor the numerator, factor the denominator. Alright, can you do that in your mind? How do you factor this? If you remember the method I had given you earlier, factor x squared and write it there x and x. Negative 2 can be factored either negative 2 times positive 1 or positive 2 times negative 1, which is the one that we need here. Because the middle term is positive, the bigger number must be positive. So, we're going to factor x squared plus x minus 2 is x plus 2 times x minus 1. X squared minus 1 is x plus 1 times x minus 1. And you notice the x minus 1 will cancel, leaving us x plus 2 over x plus 1. And now, this is actually continuous at x equal to 1. Our c value is 1. Although this is not continuous at x equal to negative 1, we are not looking for the limit at x equal to negative 1. We are looking for the limit at x approaches 1. So, since it is continuous at x equal to 1, we can replace our x by 1 now and find that limit. That will be 1 plus 2 over 1 plus 1. That is 3 over 2. The limiting value of this function when x approaches 1 is 3 over 2. And we did that by removing the discontinuity. I want you to practice this. Another one. Remove the discontinuity and evaluate the limit. Limit x approaches 3 of square root x plus 1 minus 2 over x minus 3. Well, this is a unique example. And the only way to simplify this is the understanding that the numerator square root x plus 1 minus 2 can be simplified if you multiply it by its, well, sort of like the conjugate. Now remember, a minus b times a plus b is a squared minus b squared. Now if you have some situation like that, we can remove the square root sign by doing that. So what we will be doing is, in this case we have a discontinuity at x equal to 3, and therefore replacing by x equal to 3 is meaningless, because we want to find the limit when x approaches 3. And you know that at x equal to 3 we have a discontinuity. Therefore you cannot replace x in here by 3. And that means we should try and remove that discontinuity. Alright. What we're going to do is, we multiply the numerator and denominator by square root x plus 1 plus 2. Look at that quantity. And I want you to understand it like this. If this is a and this is b, this is a minus b, then this will be a plus b. What is a minus b times a plus b? It's a squared minus b squared. And that's why we are doing this. So we multiply the numerator by this quantity and also the denominator by the same quantity. Now look what we have done. Multiply the numerator by square root x plus 1 plus 2, and multiply the same at the denominator. And now, what is the numerator now? Can you tell me? This is a minus b times a plus b, and it will be a squared minus b squared. The square of this minus the square of this. What is the square of square root x plus 1? It is x plus 1. That's right. So it will be x plus 1 minus the square of 2 is 4. I hope you understood that. This will be a minus b times a plus b. It will be a squared, square root x plus 1 squared is x plus 1 minus b squared. And the denominator, we didn't do anything there. We will leave it at that. Now, what will we do? And that will be, if you simplify this, the numerator now is x plus 1 minus 4 is x minus 3. And look at that. That x minus 3 and that x minus 3 goes. By removing that x minus 3 from the denominator, we are removing the discontinuity. That's right. So that becomes limit x approaches 3, 1 over square root x plus 1 plus 2, because these have cancelled. And now, if you look, there is no discontinuity at x equal to 3 for this quantity. Therefore, we can find the limit by replacing x by 3. That will be 1 over square root 3 plus 1 plus 2. And that will be square root 4, which is 2. 2 plus 2, that will be 1/4. So the limiting value of this when x approaches 3 is 1/4. That's a beautiful problem. Try